Let's get underway. Our opening speaker, our keynote speaker, is Dr. Raymond Richards from Darpa. Dr. Richards joined Darpa from Rockwell Collins Advanced Technology Center, where he led a research group focused on automated analysis, cyber, and information assurance. In this role, he helped foster the industrial use of formal methods verification to support security accreditations. Dr. Richards holds Master of Business Administration, Doctor of Philosophy, and Master of Science degrees in Electrical and Computer Engineering, as well as a Bachelor of Science degree in Electrical Engineering, all from the University of Iowa. He has 9 publications in the area of formal methods, software security analysis, and 1 patent. Without further ado, let me welcome Dr. Richards, and he'll be talking on the role of design languages and tools in building secure systems. Dr. Richards.
Good morning. Yes, I have 4 degrees from the University of Iowa. That might make you think I'm a bit of a fan of their sports teams. But my youngest son is currently an intern on the football coaching staff, so my wife and I have become super fans. So I'm a program manager at Darpa, and I run programs largely in software assurance, mostly focused on cyber issues. Last year, the DoD published this document, which was the DoD's digital engineering strategy document. And this strategy document points out some goals and focus areas. I don't want to read the goals, but a friend of mine in Army's Future Command characterizes the aspiration of this document is to move the DoD industrial base away from document-based engineering to model-based engineering, meaning that the outcome of engineering activities should not be human-readable documents that feed into the next engineering activity. It should be design models, and the design model should be the authoritative source of truth about the system. And if you think about that phrase for a bit, you would think that the implementation, the actual artifact, would be the authoritative source of truth. And what this sort of implies is, no, that's not true. If the models and the implementation disagree, if the implementation's wrong, and they should match the models. Now, since this is a strategy document, this is more aspirational than anything else, meaning as many people dealing with the government realize, it has no teeth unless it's in the budget. This is simply a kind of guiding star for where the DoD would like the industrial base to go. We have a bit of time to get there, and a long way to go. And to contrast what's going on, I've talked to a number of defense primes who all claim to do model-based engineering, model-based systems engineering. And if you poke at them and you find their model-based engineering is very thin. And I've got one of them to say, well, we really use modeling tools to make pretty diagrams to go into our documents. And once we do the modeling, we have the diagrams, we set the models aside, and we do the real engineering. And it's not very long before the design and the models they diverge quite quickly. And it's very painful for them to realize that they're not really doing model-based engineering. And we're working with a company that's in this state and on one of my programs, and I'll talk about that some more. And we're trying to figure out how to move them from traditional-based engineering approaches to model-based engineering approaches. So the 2 programs I'm going to focus on are HACMS and CASE. HACMS is a completed program. We're still working on some transition activities, and it stands for High Assurance Cyber Military Systems. And its focus was, how do we build cyber-hardened software for embedded systems from the ground up? And we claim that we were successful. And why did we base our claim of success? Well, we started with baseline systems, and the pictures on here, the helicopter and the truck, were the baseline systems. So Kathleen Fisher, who's now at Tufts University, started this program, and she had the great wisdom of focusing on unmanned systems. Well, because they were sexy. They're sexy now, and they were sexy in 2012 when this program started. But we gave these baseline systems to penetration testers. They were quite easy to subvert. In a small number of hours, these unmanned systems were under the control of somebody other than the authorized users of these systems. And fast forward through the program, at the end, we delivered modified systems back to the same penetration testers, and we told them go and gave them 6 weeks. And 6 weeks went by, and they came back and said, we couldn't subvert them. But if we had more people, time, and money, we're certain we could do something. Well, that's probably true. If they had more people, time, and money, if they had infinite resources, they're likely to be able to figure out how to subvert these systems. And 6 weeks may seem like a short time, but you have to realize they had all of the source code, all of the design documents leading up to those 6 weeks, so that it wasn't like they were starting flat-footed when we said go at 6 weeks. They had assessed, they had penetration tested these systems numerous times over the 4.5 years of the program at every phase boundary. They came to all the program meetings, they had all the design documents, they were intimately acquainted with these systems, and they, as I said, they had all the source code. So they had a good advantage in trying to break into these systems, and were unsuccessful in the 6 weeks allotted. To bring about this magic, we divided the program into the problem into 3 spaces. The underlying system software, and we define that to be the OS kernel, of course, but anything that interfaces with the hardware. Then the application level code, which is more specific to the platform and not as reusable, and then finally the architecture. Now the CASE program, which is currently executing, is Cyber Assured Systems Engineering, and it is a cyber program that's not considering building new software, which some people have a little difficulty with conceptually to start with. And it's also a cyber program that's cyber defense program that's not bug hunting, not trying to patch software. So what we're looking at is how do we make systems cyber resilient? And I'll define cyber resiliency in the terms of mission assurance. So how do we continue to execute the mission? The Wikipedia definition for cyber resiliency says, how do we continue to deliver the intended outcome in the face of adverse cyber events? So that's what we're trying to do on the CASE program, and we're really looking at what I'll call the left half of the engineering V. So through system design and architectural principles, how do we provide cyber resiliency much the same way we do with safety. So we think of safety, at least in a software sense, we can think of safety as tolerance of single random independent faults. Now as we move to cyber, we lose the assumptions of single random and independent. So how do we make the software more tolerant of a broader class of faults? So what I'm going to do is talk through several of the technologies that came out of these 2 programs and how they relate to various language technologies. And I'll start with VST, Verified Software Toolchain. This was developed by Professor Andrew Appel at Princeton. This works with Verified C. So his notion was we need to be able to come up, we need to be able to verify C code at the source level and run it through a verified compiler in order to get very high assurance implementations. And he had worked on this for some time before the HACMS program began, as that diagram indicates. And going in, the interface between the retargetable separation logic and the compiler was kind of broad, meaning they couldn't do everything they wanted to do. They couldn't build the sorts of systems that we needed on HACMS. Specifically, separate compilation, real-time, real system calls, and shared memory concurrency were difficult to handle with this tool set, and we we've overcome those shortcomings on the HACMS program. So what we used this for was to develop verified crypto components. So this is how we harden the command and control links for these vehicles, and mailbox messaging systems to move data from one partition to another. We ended up developing partitions to separate concerns on these unmanned vehicles, and it used a verified mailbox messaging system in order to bring information from one partition to the next. One of the things we got a great deal of mileage out of was something that the programmer, the performer, called embedded domain-specific languages. And what they did was they started with what I'll call a modern functional language, and they used Haskell as the language, as the host language. And they believe they could have started with another host language, and they looked at Rust and some others. But they were Haskell people, so they started with Haskell, and they embedded a domain-specific language within the syntax of Haskell. So what does that mean? Well, they wanted to use the advantages of Haskell, meaning formal semantics and type safety, but they wanted to provide extra protections, especially around the interfaces. They wanted to provide very strong guarantees around the interfaces. So they built a smaller compiler that provided additional checks on the interfaces and compiled Haskell into C, and then C into the target system. So the advantage is they got guarantees, cyber guarantees on the interfaces using their small compiler. When I say small, it was implemented in 8,000 lines of code. And they used a C compiler to target various other backends. They essentially used C as an intermediate language without having to implement all the backends to the different sorts of platforms we were targeting. This also allowed them to use a variety of different verification tools on the high end, on the Haskell side, and they had guarantees that their small compiler was faithful to the embedded domain-specific language. And honestly, this is what we used for most of the program. We got the most benefit on HACMS from implementing the helicopter codes. We worked on the unmanned variant of the Little Bird helicopter. The Little Bird's a small two-place helicopter favored by special forces. Boeing has an unmanned variant of it. We re-implemented almost all of the mission computer code in Ivory. Another thing we did was come up with specifications of control systems and generate provably correct implementations of those controls. We did this in a language called Chimera and using a tool called High Assurance Spiral. So you could give Chimera, these are the control equations for this real-time, for this cyber-physical system. Here is a safety condition we want to say holds true. It will produce proofs and an implementation that correspond nicely with each other, meaning they're proofs that they correspond and proofs that they're correct. So we did some interesting things with this. First, the helicopter had no idea when it was on the ground. So there was no physical signal in the unmanned Little Bird that told it you have weight on wheels, or weight on skids in this case. And the reason was that, of course, they had switches on the skids that sent signals, but helicopters are they vibrate a lot, and they got a lot of nuisance switches, so they couldn't rely on the switches to tell them they're on the ground. And I said to the Boeing guys, you guys really have an unmanned helicopter that doesn't know when it's on the ground? How do you overcome that? They said, well, we just assume intent. If we intend to be on the ground, we assume we are on the ground. Which is a little scary, and you could well imagine if it being used on a resupply mission or a medical evac mission, and if an adversary wanted to cause trouble, they could put a boulder or a block under one skid and cause it to flip over because it would just assume it was on the ground at some point. Another thing we did with this was the unmanned trucks. So those Army trucks is something being developed by TARDEC. The notion is the Army would like to have far few drivers in a convoy than vehicles. And they thought the autonomy problem is easier if you're just doing a safe following of the vehicle in front of you. So one of the safety properties we built into the controller of that was you're not going to run into the truck in front of you. We developed control laws that provably respect that property, and I presented this to the Marine Corps, and the Marines said, why would you do that? Sometimes we run into things on purpose. If there's a roadblock, we're going to go through it. So I thought it was interesting that we thought it was an obvious safety property. The end user thought was a nuisance. And this slide, I'll start to bridge from HACMS into CASE, and this is where the two programs overlapped. And I mentioned the highest level in the hierarchy on HACMS was architectures. And that's really where we're focusing on CASE. And this is really the touch point with our friends in the defense industrial base who do very thin model-based development. I'll give you the punchline. We use AADL quite a bit. We toyed with SysML as an architectural language and found SysML is a fine language if you're talking about system level requirements. But as soon as you start looking at software for a distributed, embedded, real-time system, you need to move away, or you need something richer than SysML. And we found AADL to meet our needs nicely. And it's being picked up by Army Futures Command in future vertical lift platforms. They have they had an AADL Users Day a couple weeks back, and they had the performers for their future attack and recon aircraft all very interested in how do we use AADL. Most of the tools developed on HACMS and on CASE are being integrated into OSADI, which is the open source AADL tool environment supported by SEI. So they're sort of the keepers of the AADL standard, and they're supporting AADL with this open source tool environment. We've developed a lot of plugins that fit with their environment, and so if you download OSADI, you get a lot of the tools developed on HACMS and on CASE. But unfortunately, AADL is not as prevalent in the industry. As I said, a lot of the defense contractors use SysML. They think they're doing model-based engineering. And they don't want to lose, they want to continue to look at the system level in SysML. They like some of the pretty pictures they're getting out of SysML, and they don't want to lose that work. And importantly, they don't want to have to do the modeling work twice. So we need to come up with translators that allow us to harvest what's been done in SysML and pull it into AADL. And extensible languages are a must. And we use the extensions on AADL quite prevalently. We've come up with several annexes. The AGREE annex, supporting the AGREE tool, assumes guarantees reasoning environment and allows us to do compositional reasoning over contracts of components. Another annex we use quite heavily in both programs is one we developed called Resolute. And Resolute is an assurance case tool. You can think of it as an assurance case language, not too dissimilar from goal structure notation, but it's tied to the architecture. So you have the assurance case expressed in terms of the architecture. It allows you to evaluate the assurance case argument in the context of the architecture. If the architecture is changed or updated, it will invalidate parts of the assurance case. One of the big advantages of using architectural language is it allows you to start to leverage architectural patterns. This whole notion of doing digital engineering and architectures is starting to show up in new Darpa programs. There's a program that's in source selection now called, what is it called? Symbiotic design. And the notion is we'll use machine learning and artificial intelligence to allow human designers to more efficiently, effectively, and completely explore the design space and come up with more innovative and more on-point designs than the human designer would come up on their own. And this is through the leveraging of architectural patterns. We are also using it on the CASE program to support cyber resiliency. So architectural patterns we've been playing with include the insertion of runtime assurance components that allow us to identify when something's gone wrong within the internals of a system and signaling to the system that that something's amiss. And you can think of it as you're an architect, you have a high-level property you're trying to design into the system. You're finding it difficult to prove part of that property on some part of the system, and you want to be able to say, I assert that this sub-property holds here, maybe where the filter is in the bottom left. And the filter in that case is, let's talk about the monitor. The monitor on the right, the monitor is that we're getting only valid GPS coordinates into the system. And there's not just raw from the radio, but there's a GPS processing process out in the world that's taking the GPS signal and decoding it and producing what it thinks is a correct GPS location, and it's going through the system into a more critical part of the system, the flight controls, that's using that data, and we're asserting that the GPS data is valid when it's coming through there. And valid could mean it's a true location someplace in the world, or valid could mean something more stateful, meaning this location is feasible given the previous location I knew I was located. So we're using that runtime assurance to avoid having to completely analyze part of the system at design time. And that provides us the ability to recognize when something's gone wrong. If we're getting an incorrect GPS location at that point in the architecture, it's likely not a hardware fault. It's likely that something's been compromised and is spoofing locations to us. And the hypothesis is having to check well-formulated mathematical properties in the internals of the system is better than intrusion detection or anomaly detection, because by definition, you don't know what an anomaly or an intrusion looks like. But if you have a closed form property you're checking, you're going to be able to determine if something's gone wrong, and more importantly, the designer has a fighting chance of understanding how to recover from it. So that's how you get the kind of fight-through attitude or position on cyber resiliency. You can affect recovery and perhaps continue in a degraded situation. So in the CASE program, we're developing libraries of cyber resiliency supporting patterns and anti-patterns. So I have an academic performer at Rochester Institute, who's using trained classifiers to go over a large corpus of design models, and are looking for what sort of patterns in these models support resiliency. What sort of patterns are strong, and what sort of patterns really work against us or are weaker. And the idea is we want to be able to use these trained classifiers on real designs during design time. And I hate using the Clippy model, but you can have the Clippy pop up and say, hey, it looks like you're trying to build a cyber resilient system, but you've done this over here. Perhaps you should consider applying this pattern in place of that pattern. So we are trying to get to that point where the tools assist the designer, point out where they've made mistakes, apparent mistakes based upon the use of weak patterns and suggesting stronger or more resilient patterns in their place. And also using these specifications to synthesize as much of the system as possible. We'd like to get humans out of the loop for writing code. A colleague at Darpa likes to say humans are worthless bags of meat and soon will have no economic or military value. He says that somewhat tongue-in-cheek, but I'm a little scared that he's not tongue-in-cheek. So as we use these architectural patterns, we want to be able to synthesize their implementation directly in a correct and verifiable manner. And also we want the model to correspond to the implementation in a nice way. Unlike our friends that I mentioned in the industrial base who are using SysML to make pretty pictures and then develop the implementation without ever consulting the model again, we want the model and the implementation to correspond completely to support this notion in the digital engineering strategy that the model is the authoritative source of truth. So synthesizing the glue code. So some people I brief at the Pentagon don't understand glue code, and I tell them, well, that's the arrows in your box and arrow diagram, but it also marries it to the operating system and the platform and implements all the separation and data flow that you have in the system. One of the goals in the CASE program is to develop something I call explainable formal methods. And explainable formal methods, I give an intuition what that means in that oftentimes in a model-based design environment, you have a deep chain of tools. You'll have some high-level model the human's working in. Then that gets translated perhaps to another model, gets fed to a tool, translated to something else. There's a model checker called on that underneath the covers. That's calling a SAT solver. Pretty soon the SAT solver comes up with a response. Hopefully it proves the property, but if not, and if you can get any information out of the SAT solver, whatever it tells you is a long semantic way away from what the human designer worked in. So how do we get rich, actionable feedback to the human designer in kind of the abstractions the designer thinks about? So if you have a SAT solver that produces the it can't come up with this, a solution but has an unsatisfiable core, if you could communicate that back to the human designer, he's not going to know or she's not going to know what it means, right? You have translated the problem into perhaps some Boolean equation that's very deep, and there's no solution for it. Well, that doesn't mean anything to the person designing a helicopter or a truck or other embedded system. So how do we get that feedback back to them? One approach being developed by an industrial performer with an academic partner, and the academic partners are Cesare Tonelli and Clark Barrett. Tonelli at the University of Iowa, Clark is at Stanford. And I bring up those two because they're sort of the fathers of SMT, and they developed a CVC4 SMT solver, and they told me that this approach is just an extension of that philosophy. And what they're trying to do is use meta-reasoning. So they want to translate the model and the query into an intermediate language they call intermediate modeling language, or IML, which they've released openly about 6 months ago, and do reasoning over the query and the meta language to determine what's the best way to approach this analysis query. What is the best arrow I have in my quiver for doing this, not only to shorten execution time, but provide the best feedback. And they'll call that tool, get the feedback, and they'll lift it kind of in steps, hopefully to let the user know, hey, if this property was proven out, what parts of your system, where was the goodness that helped this? So if you are modifying the design, you don't happen to perturb something you were depending upon on this property you've already proven. Or more likely the case, it was inconclusive. You could neither disprove or prove the property. The tool just didn't respond. Where are the likely subjects in the design that need to be addressed, and how do we get those back up there? And this is done through their intermediate modeling language. So they're making great headway on this. They've reported that by the time they decompose a query and push it out to the best-of-breed tool, they're getting significant feedback or improvement over just using a very broad tool that's sort of good at everything. If they use a specialized tool, they've seen up to 97% improvement in the execution speed and the nicety that they're getting feedback to the designer in design abstractions instead of analysis abstractions. So in conclusion, I think we're going to see drastic changes in how we engineer embedded systems, and as pointed to by the digital engineering strategy. And I say drastic because looking at the industrial partners I've talked to and their use of, I'll say, skin-deep modeling and walking away from the model in order to go about the real work of engineering is not what the Department of Defense wants anymore. They want to keep the digital artifacts over the life cycle of the system and be the authoritative source of truth of the system. It sort of means we're moving away from the traditional engineering V. And the engineering V implied that verification was a separate activity from design. And I think verification and design are going to become one and the same. And I have a colleague who likes to say verify early, verify often. And I have to give him a quarter every time I say that. So there's that. But I think that's true. We're moving into an era where verification is going to become continuous verifications over the course of not only the design and implementation of the system, but then over the life cycle system as it's sustained and modified. The verification is going to be part and parcel to the entire life cycle. But this requires the ability to manage, analyze, and move data among models that span that life cycle. And I think there's a great deal of work in order to get us to that vision. So modeling language are going to be the backbone of this. So I mentioned AADL is a great language for doing architectural modeling of real-time embedded distributed systems. But it can't do everything. On the case program, we have a performer who's trying to lift binaries into AADL, and I still raise my eyebrows at that. So literally, they are taking software binaries and modeling the binary instructions in AADL. They're doing this largely to be able to take properties from the rest of the program and analyze them directly. But as you can guess, the models are huge, many times bigger than the binaries that they're modeling. Even on small binaries, they quickly run out of space. So we're going to need an interlocking mosaic of design languages with ways of translating between them that are robust and believable. And we need to invest in research on how are we going to reach this vision, and how are we going to leverage these design models over the lifespan of the system, as the strategy clearly points to. And with that, I've got about 10 minutes for questions.